high-end hardware. I'm talking about hardware that's even below what we consider the recommended spec of GPUs. So, all right, so those are those two techniques, and I don't have too much time to talk about them more, but that's just a good primer. I think something to think about. How do you reduce fill rate at the periphery for those pixels that we are over-rasterizing by default? So let's talk about reprojection just for a few minutes. Reprojection is something that is the best method we know of today for dealing with dropped frames, for dealing with missed frames. Okay. If your engine's not hitting frame rate, the VR system, the underlying VR system, really only has one option to fill in that dropped frame, and that's through reprojection. Now, by reprojection, Oculus uses the term time warp to refer to rotation-only reprojection, I believe. I hope I don't have that wrong. And then, but there's also ways to do position and rotation reprojection by using a depth buffer, which I'll talk briefly about. Reprojection is fine for filling in missed frames, I think, but you really should think about that as a last resort safety net. You absolutely should not rely on reprojection to maintain frame rate on whatever your application says is the min spec. If you tell your customers, this GPU is our min spec, you should not rely on reprojection to maintain frame rate. I think that's a bad idea, because there's artifacts, visual artifacts that come with reprojecting. So let's talk about that, because I think it's important to discuss what the side effects are of reprojection, so you can make good choices about when you think it's okay for your application to use it. So the most obvious artifact is Judder. Hopefully everyone here already knows what Judder is. The idea is that anytime there's animation, you're rendering at half frame rate, and you're filling in every other frame with a reprojected frame, you're going to get what looks like two ghost images overlapped. And that's going to, and we call that Judder, and that you can get that either from the camera translating, if as the user you're moving around, translating, squatting, standing, you're going to see a ghost image of what's in front of you. If you're standing still and something's animating in front of you, the animation's going to have basically two clear ghost images that are overlaid. And the farther apart those ghost images are based on how much movement there is. And of course, if you have track controllers and you're holding stuff right in front of your face and moving it around, they're going to ghost pretty badly too. But it's not that obnoxious. It's a ghost. It's not as bad as actually rendering at half frame rate and not reprojecting. So that's a known side effect. That's not as big of a deal, I think, as these next issues. These side effects are the ones that sort of worry me more. It's the more subtle side effects of reprojection. And the idea is that when we talk about rotation-only reprojection, if you don't really take the time to think through what that means, you might misunderstand what's really happening. And so when you reproject, the reprojection is eye-centered, not head-centered. Your head, when it rotates, is head-centered. And so when you render an image, so these are this is a top-down view of two eyes and what they're looking at. And this is our left and right virtual cameras rendering their parallel frustums. Now, if you're going to reuse the output of those rendered frames as you rotate your head, what's going to happen is your eyes are going to change position as your head's rotating and looking left and right. In this example, it's an extreme rotation. But what happens is, you can see really clearly, is that we're using those frustum that we rendered with. They're frozen in time. Those images are rendered. We want to reuse them. So what's happening is you're actually fetching from images that were rendered for one eye, potentially from in front of your left eye and from behind your right eye. And this is really bizarre if you think about it from a rendering perspective, that there's this sort of scaling effect that you're going to get. The more rotation that there is in your reprojection, the more of this really subtle scaling artifact you're going to get. So, I'm worried a bit about that as far as the reprojection effects, but not as much as this next thing, which is your ICD. So IPD is how far apart your eyes physically are. Your ICD is your intercamera distance. It's your virtual camera separation that you render with. Generally, you set your ICD to be the same as your IPD, right, as your physical eye separation. So in this example, the user has 64 millimeter separation of their eyes, so you set your virtual cameras at 64 millimeters apart. Now, in the same extreme rotation as above, if you rotate your head, which looks like maybe about a 10 or 15 degree rotation, what's going to happen is that ICD is going to artificially narrow. If you take the two vectors that are pointing straight ahead of those eyes, they're going to be artificially narrowed. And so what happens is the more you're rotating, the more you're reprojecting, the more you're reprojecting, the more your ICD, your virtual cameras, are artificially narrowing and widening. And I'm worried about that effect on the human visual system, on your perception system, also known as your monkey brain. And I'm worried about what that does to users long term or over long periods of time. So we tend to think about rotation-only reprojection as something that we really just want to use to fill in dropped frames occasionally. And when you think about how bad of an error is this, so Mike Abrash, in one of his Valve blog posts in 2013, I think had a really good statement, which is a leisurely head turn is in the ballpark of about 100 degrees per second, which is about this, you know, and you can obviously rotate faster, 200 or 300 degrees if you're whipping your head fast. And if you reproject just one frame, you'll probably go 2 or 3 degrees worst case. If you're going to reproject multiple frames in a row from that same render, that's going to double. So you can easily start reprojecting 5, 6 degrees or more. And that's where I start to get worried about these subtle side effects of reprojection. So those are the side effects, but there's good things about reprojection. Obviously, it's a well-understood algorithm. We've known it for decades. It's not, you know, it might actually improve. There's people looking at ways to improve rotation-only reprojection given these side effects. It works reasonably well for a single missed frame. It just does. You know, even with those side effects that we're aware of, for filling in dropped frames, it works reasonably well. And my personal statement is that there's clearly a non-trivial set of trade-offs, but I think it's good enough to use as a last resort safety net to fill in dropped frames. It's better than dropping frames and rendering at 45 hertz. That goes without saying. I hope everyone in this room already agrees with that. Rendering at half frame rate is not shippable, it's not showable. It's very uncomfortable to your users. So it is a usable solution. Positional reprojection is one that's a little trickier. I'll just touch on this lightly. It's obviously, I think, it's still an unsolved problem to some degree. We're super interested in a solution to this because if you can do positional reprojection and you can actually take into account the new positions of the eyes and the head as you're moving and effectively have a depth value per pixel, that's going to produce a better result. But there's some issues, right? In a traditional renderer, you only get one depth value per pixel. So if you have translucency, like particle systems, good luck reprojecting that. They're going to be set at the wrong depth. Okay, so you can't just use a traditional renderer and have it just work magically. You know, there's issues with translucency and depth there. Another subtle problem is if you're using MSAA, your depth buffer is going to be stored as multiple samples per pixel. But you may have already resolved the color buffer. So now if you try and reuse that resolved color buffer with those separate MSAA rendered samples, you might get color bleeding. If you have a near surface and far surface of very different colors, they're going to blend together, and when you reproject, you're going to get color bleeding across surfaces that are nowhere near each other in space. Hole filling algorithms, obviously, as you move around and you start peeking around corners or you squat or stand and you look over surfaces, there's going to be pixels that you have no data for, so you have to invent a color for those pixels. We call it hole filling. And you have to be very careful because a lot of these algorithms can cause retinal rivalry, which means your eyes can't stereo fuse those colors because they don't match. And so it's a very tricky problem. It's a hard problem to solve, but it's something we've been thinking about because that'll have far fewer side effects than doing rotation-only reprojection. So then there's asynchronous reprojection. Asynchronous reprojection is the idea is that you can have a job on the GPU that, let's just say, half a millisecond before vsync, no matter what's going on, the GPU gets interrupted, you preempt the GPU, and if the currently rendered frame is not done, it can take last frames, left-right stereo pair, do a reprojection, rotation-only reprojection, and display that, and then let the GPU continue on finishing the last frame. We think this sounds like the silver bullet, the ideal safety net. If you have a system like this, then we can practically guarantee that we never drop frames on an HMD, which is super critical for consumer VR. But it requires preemption granularity on the GPU that's as good or better than current generation GPUs. I meant to ask AMD and Nvidia what I can and can't say about their GPUs publicly, so I'll stick to what I believe they've already said, which is current GPUs, current generation of GPUs, we can think of it as you can generally preempt at draw call boundaries. It's not entirely true. You can go a little slightly finer, I think. But you can preempt at draw call boundaries. That means if you want to step in and reproject at the end of a frame, and your VR system says step in half millisecond before vsync or 1 millisecond before vsync, if there's a really expensive draw call happening, like you have a 2 millisecond post-process call, well, what's going to happen is it won't be able to preempt in time, and you're going to miss vsync. So there's really no guarantee with current GPUs, the way you can preempt, the granularity, there's no way to actually guarantee you can preempt and get there in time. You have to play a lot of games with timing. So The applications have to be aware of preemption granularity for current-gen GPUs for asynchronous reprojection to be a real option. And I think Nathan Reed from Nvidia had a great thing to say at GDC last year. His statement is, if you think about post-processing, if that is an expensive draw call that could be blocking and not allowing preemption to happen, break your post-processing up into a bunch of smaller triangles and render triangle at a time with individual draw calls, right? Give the GPU and give the drivers more opportunities to be preempted. But you know, again, there's situations where you have track controllers, right? I can go and pick up something the size of a marble and put it right in front of my eyes, and now that's a full screen render of this little object that you wouldn't have imagined would be full screen, and that marble could be really expensive to render. So, you know, there's no great solution yet until GPUs can be preempted instantly. We're at a much finer granularity anyway. So we have this thing called an interleaved reprojection hint. So the reality is there are going to be GPUs and older GPUs that we care about that cannot support asynchronous reprojection. So we need something else. We need an alternative. And so we have this idea. So we have this. We just added this to the OpenVR API recently. It's an interleaved reprojection hint, and it's a hint in that we can request that the VR system opt into an every other frame rotation-only reprojection if the underlying system doesn't support asynchronous reprojection. That's why it's a hint. The Valve programmer that's been writing all of this code, his name's Aaron Leiby. He's done a really interesting implementation of interleaved reprojection. It's incredibly detailed and tricky to get right. There's a lot going on in how you predict properly where you reproject, what your timings are, and he's got this to what I think is a really optimal implementation where instead of having 11 milliseconds for a frame, when you opt into this, you end up with having almost another 2/3 of a frame at your disposal, so you have about 18 milliseconds to render. So this is a great safety net. It's a good bottom of the barrel. Once you're at the bottom of your quality level, we'll talk about adaptive quality in a minute, you can opt into this and buy yourself an additional 7 milliseconds to render. So we think that's a good safety net. And it's also a safety net that the runtime could opt into, could automatically turn on when it detects your app's about to drop frame rate. We can just force this on if there's no asynchronous reprojection support on the GPU that you're rendering or in the underlying system. So it's a good trade-off, I think. It's a good trade-off, and I agree with what Michael Antonov from Oculus said last year. He has his blog post from March 2015. If you haven't read it, read it. It's a really good post. It's titled Asynchronous Time Warp Examined. And what he's saying here in this paragraph effectively is, I'll summarize it here, is asynchronous time warp should run at a fixed fraction of the game frame rate. Meaning, if you're at 90 hertz refresh rate on the HMD, you either want to hit 90 hertz or fall down to the half rate of 45 hertz. And this is going to result in image doubling, Judder, but the image doubling is going to be stable because it's the same separation frame to frame. If you target some intermediate frame rate or a variable frame rate, that Judder ghost is going to jump all over the place, and it's going to be a far worse effect. So I think everyone's on the same page here that an interleaved reprojection, that approach is the right approach to fill in dropped frames if you need to use that. All right, well, that's what I want to say about reprojection for now. I'll come back to that in a little bit. Now let's talk about adaptive quality. This is what I really want to talk about. And I'm going to pull those other 3 sections into this. So maintaining frame rate in VR is really hard. It just is. It's way more challenging than non-VR rendering, in my opinion. And the reason for that is because there's 2 main reasons. The first is that the users have fine control over where that camera is. If you think about a traditional game, first-person shooter, you're pretty much a standing height or crouching height, and you're moving in a plane. And it's pretty easy to figure out all your perf problems. And you also have this big bounding bubble around you, so you can't really walk up to walls that close because we're good at our jobs. But there's limitations that help us and makes it really easy to keep frame rate. In VR, users can put that camera anywhere they want. They are fully tracked in that space. A couple weeks ago, I was laughing. We were giving a demo, and someone was looking at the robot repair demo. I look over at the guy. He's literally laying on the floor, looking up at Atlas. Like, what are you doing? What are you? I just want to see what it looked like from down here. I was like, great. I have no idea what the perf is down there. I've never done that. Other people have come through the office that are like almost 7 feet tall, looking down at Atlas, and I'm like, oh, I don't know what that perf's going to be like. I've never tried that angle, right? I'm not that tall. So the users have a lot more control over that. And additionally, we have track controllers. A lot of experiences are letting users effectively reconfigure their environment. With track controllers, you can pick up objects, move things around, and if you put 100 objects scattered around a room, someone's going to take all 100 of those objects, make a pile of all those objects, and shoot a rocket at it just because it's going to be fun, right? And so it's hard to anticipate performance. It's hard to really fine-tune performance in your engines in VR because of the interaction models that we're moving to, especially with track controllers and being able to move things. So I have personally given up on trying to tune a renderer and content to hit 90 hertz. I went through that pain last year. We showed robot repair last year at GDC. We haven't really changed the content or shaders at all since then, by the way. It's the same demo. But before GDC last year, I spent a ton of time, and everyone in the room's done this, you take the worst 20% of that application, of that experience, and you tune your performance of your renderer, of your code, to hit frame rate for the worst case scenario. And the other 80% of your experience is in frame rate. It's not a big problem, right? The problem, though, is that that was barely hitting frame rate on 980. It maintained frame rate. I didn't fail. It hit frame rate, fine. But if you dropped any lower GPU in that and run Aperture on it, it wasn't going to hit frame rate. And so thinking about how to manage that and get to a shippable solution led me to think more about this adaptive quality system. And so that worst case 20% is what really drives our decisions usually. So I wanted to think about this differently. So adaptive quality, to state it simply, it's a way to dynamically change rendering settings. I'll explain what that means in a second. Rendering settings to maintain frame rate while also maximizing GPU utilization. You want to be able to scale up, right? So there's two goals with this. The first goal is to scale down, to be able to reduce the chances of dropping frames